In the context of robotics, the concept of developmental scaffolding is explored using large language models, LLMs. Inspired by parental scaffolding in infant development, researchers investigate whether LLMs can guide a robotic system in learning to predict the effects of its actions. The setup involves an object manipulation scenario where one object can be picked and placed on top of or near another object. The adopted LLM, GPT 3.5, generates state descriptions and action alternatives in natural language, guiding action selection. Simulation experiments show that LLM-guided learning yields significantly faster discovery of novel structures compared to random exploration. However, GPT 3.5 struggles to effectively guide the robot in generating structures with different affordances, such as cubes and spheres. The results indicate that, even without fine-tuning, LLMs can serve as a moderate scaffolding agent for improving robot learning, but they lack affordance understanding, limiting their applicability in robotic scaffolding tasks. The importance of exploring complex environments, where random exploration may not be sufficient, is highlighted. LLMs are proposed as a scaffolding agent to accelerate skill and knowledge acquisition, leveraging their capabilities in generating human-like natural text and code-like structured text. The limitations of random exploration are discussed, citing previous work on effect prediction and planning. Conditioning LLMs for the agent's embodiment is crucial to perform grounded inferences in robotic settings. Different strategies for descriptive embodiment alignment are highlighted, including bottom-up skill learning, prompt engineering, and the use of multiple modalities. Overall, the study demonstrates the potential of LLMs as a scaffolding agent for robotics, but also identifies the need for further research to address the limitations of current LLMs in affordance understanding and grounded reasoning. The proposed research utilizes large language models, LLMs, as a scaffolding agent for robotic learning in tabletop manipulation environments. Inspired by infant development through parental scaffolding, this method leverages the high-level knowledge in LLMs to guide and accelerate robot exploration and learning. Specifically, GPT 3.5 is used to select actions that may lead to interesting or novel outcomes, aiming to create a system capable of making grounded inferences. To validate this approach, a simulated robot, UR10, is used in a tabletop environment where task complexity can be adjusted by varying the number of available actions and objects. The robot's interactions are simulated using the Pi-Bullet simulation library, focusing on pick-and-place actions to interact with objects on the table. Each session consists of 10 interactions, starting with a random initialization of cubes and spheres on the table. The robot selects a source and target object, executes a pick-and-place operation, and records the outcome. The available actions are characterized by 3 integer tuples, indicating the source object id, target object id, and discrete relative positions, including top, next, and front positions for stacking, displacement in the positive y direction, and displacement in the positive x direction, respectively. The efficacy of the proposed LLM-guided scaffolding method is tested against a random exploration baseline in different environment configurations, measuring exploration efficacy by the visitation frequency to hard-to-reach states, such as tall towers. The results show that GPT 3.5 can actively lead the exploration to hard-to-reach states and demonstrate the effects of different prompt structures and the capability of making grounded inferences when different types of objects with different affordances are introduced. Large language models, LLMs, are being utilized for scaffolding robot action exploration, enabling the selection of actions based on given prompts. The system prompt conditions the LLM to choose an action that leads to an interesting outcome, while the user prompt informs the LLM about the environment configuration. In experiments, the LLM's scaffolding is compared with a random exploration strategy, demonstrating that the LLM discovers complex structures, such as towers, significantly faster. These experiments vary in terms of the number of objects and possible actions, showcasing the efficiency of the LLM in different scenarios. This approach highlights the potential of LLMs in enhancing robot learning and exploration capabilities, particularly when dealing with complex tasks and environments. The use of LLMs could revolutionize the field of robotics by allowing for more efficient and effective exploration strategies. The authors present 3 experiments to evaluate the effectiveness of large language model, LLM, scaffolding in accelerating learning exploration in a block stacking environment. In experiment 1, 2, and 3, they compare the tower heights achieved by random exploration in LLM scaffolding in environments with increasing complexity, featuring 4 cubes and 2 proximity locations, 5 cubes and 2 proximity locations, and 5 cubes and 3 proximity locations, respectively. Figure 2 shows that LLM scaffolding significantly outperforms random exploration, achieving taller towers, especially in the most complex environment setting. This is attributed to the decreased probability of visiting hard-to-reach states during random exploration as the environment complexity increases. The authors then investigate the effect of different prompts on the tower heights achieved. In experiment 4, they replace the adjective interesting with novel in the system prompt and conduct an LLM scaffolding experiment in a 5-cube, 2-position configuration. Figure 3 shows that the novel adjective leads to lower tower heights, as the LLM focuses on avoiding similar actions to previously executed ones, resulting in fewer complex structures. Finally, the authors examine the LLM's ability to exploit affordance knowledge by introducing a sphere into the environment alongside 4 cubes. Figure 4 shows the height distribution of sessions collected with both LLM scaffolded and random exploration policies. The results demonstrate that LLM scaffolding outperforms random exploration, achieving the tallest tower in one of the sessions, while random exploration fails to achieve the tallest tower. In the context of environmental complexity, introducing a sphere significantly increases the complexity as stacking cubes on top of spheres results in them dropping to the table surface, similar to the initial state. This necessitates the sphere occupying the topmost position, adding a constraint. The GPT-based approach successfully produces a tower with a height of 5, showcasing its ability to target hard-to-reach states. Despite LLM scaffolding showing improvement over random sampling, the expectation was for the LLM to perform similarly to an environment with 5 cubes by avoiding states where the sphere is placed on an incomplete tower. However, the LLM disregards the fact that cubes cannot be stably stacked on the sphere and actively tries to stack cubes on top of it. The GPT is conditioned to select actions based on their perceived interest, which may not lead to the construction of a tower in the long run. To assess GPT's understanding of affordances, an experiment was designed where the LLM is asked to create the highest possible tower in environments with 5 objects and 3 spatial positions. The results show that GPT prefers stacking operations and avoids deconstruction, successfully building higher structures in most sessions. However, when a sphere is introduced, there's a preference for placing it in the middle positions, which immediately increases the tower's height. This behavior demonstrates the GPT's understanding of the sphere's affordances as a stable base for future placements. Large language models, LLMs, have been increasingly explored as knowledge bases for robotics applications, but their lack of real-world experience hinders their ability to make grounded inferences. This study proposes a novel approach inspired by parental scaffolding, where LLMs act as scaffolding agents to guide robotic exploration. In this framework, the LLM provides high-level direction, while the robot executes low-level actions, facilitating the acquisition of new experiences. Experiments were conducted to compare LLM scaffolding with random exploration in various environment settings. Results show that LLM scaffolding enables robots to target hard-to-reach states, resulting in experiences with high information gain. However, when distinct affordances, such as spheres, are introduced, the performance of LLM scaffolding decreases, revealing limitations in the model's grounded reasoning capabilities. These findings suggest that LLMs can provide valuable knowledge for robotics, but a gap remains between their high-level reasoning and low-level embodiment. The study highlights the potential for future work to explore more advanced systems, such as PaLM and GPT-4, and develop methods to enhance grounded inference capabilities without incurring additional computational costs. Bridging this gap is crucial for realizing the full potential of LLMs in robotics applications. Developmental and biologically realistic modeling of perspective invariant action understanding has been a focal point of various research projects and studies. Understanding actions in a perspective invariant manner is crucial, as it enables the development of grasping and manipulation skills. This is because perspective invariant action understanding allows agents to recognize and replicate actions regardless of the viewpoint or orientation. One key approach to achieving perspective invariant action understanding is through the use of neural networks. Researchers have employed 3D convolutional neural networks to learn perspective invariant representations of actions from multi-view videos. This approach has shown promising results, with the models demonstrating the ability to recognize actions even when the viewpoint is significantly different from the training data. Another significant aspect of perspective invariant action understanding is the role of cognitive development. Studies have shown that infants as young as 6 months old are capable of understanding actions in a perspective invariant manner. This suggests that perspective invariant action understanding is an innate ability that is present early in cognitive development. Furthermore, researchers have also explored the use of reinforcement learning to develop perspective invariant action understanding. By using reinforcement learning algorithms, agents are able to learn to perform actions in a perspective invariant manner, even in the presence of complex and dynamic environments. The significance of perspective invariant action understanding is further underscored by its potential applications in robotics and computer vision. For instance, robots equipped with perspective invariant action understanding capabilities could perform tasks such as object manipulation and grasping with greater precision and flexibility. Despite these advances, there are still limitations and areas for future work. For example, current models struggle to generalize to new environments and scenarios, highlighting the need for further research into the development of more robust and adaptable models.